I'll just hide it for now.
Yeah, I will.
So we'll just check if this works. Yep.
Awesome.
So literally up and down, and you got a laser pointer there as well.
Great. I mostly only need the laser pointer.
I like to walk around the room and talk.
Yeah.
I find it makes it a lot more fun for me. But okay, so basically to go, will you need the projector at all?
Nah.
No.
Nah.
Okay. I think it automatically does it.
Yeah, it did. That's what it came up with before, I think.
Do you want me to just check?
Yeah, turn on the...
So you just press all displays,
Yeah.
and it's currently on there, so maybe just load that again. There you go.
Awesome. Great, that's perfect.
Sweet.
Okay, so I need to mic up too, right?
You what, sorry?
Need to mic up.
Oh, yeah. So, just make sure it's on. Yep. And then basically you just pin that onto you.
No worries.
Cool. I'll introduce you.
Great, let's go.
Alright. Thanks everyone. I hope you're enjoying the unit so far. This is now finished with these lectures, and now there'll be a couple of guest lectures where we give you pitch presentations and week 11 as well. So the first of those guest lectures today is by Andrew Stevens. Some of you might recognise him from the workshops as one of the demonstrators. But Andrew actually has a really strong background in this kind of area. He did his PhD in Brisbane at Griffith University on sensing and control systems. So very relevant for this kind of work. And now he's working in my lab at the Driect Institute as well as the program. So he'll be talking about medical device instrumentation, direct measurement, and just a reminder that even guest lecture material is downloadable as well. Okay, so please keep that in mind throughout the lecture. So over to you, Andrew. Enjoy, and I'll see you in the lecture.
Thank you, Sean. So yes, as Sean mentioned, my name's Andrew. I have a background in both sensing and control, and I'm working in Sean's workshop. So this lecture will primarily focus on sensors, as that's my area of expertise, but there'll be a little bit of imaging in there as well. I think you'll find this pretty useful for your next part of your assignment, because I'm going to talk about ways to deal with how to design a sensor specifically for its purpose. So let's begin. So what's going to be in this lecture? So I'll talk a little bit about me and our lab. I will talk about my past work so that you have confidence that I know what I'm talking about. I'll talk a bit about direct measurement, and we'll cover some of the basics of direct measurement, and then we'll talk a bit more about advanced techniques. We'll look at indirect measurement, which is something that you might not really be that familiar with. And then we'll look at a comparison of direct and indirect measurement and an outlook on where I think everything's going to go. So, about me. As Sean mentioned, I graduated in an undergraduate of electronic engineering from Griffith, and then I did my PhD in sensors and control of ventricular assist devices, which most of you should know about. So now I work in Sean's lab. I'm looking at quality of life outcomes for ventricular assist device patients. I'm looking at automatic control of ECMO and VADs. We're looking at improved monitoring of patients receiving CPR to try and make sure that they have good neurological outcomes. They don't come back with brain damage, and also many other projects involving VAD and ECMO. And I have two dogs called Artemis and Olive, sausage dogs. So a little bit about Create Lab. Maybe Sean's mentioned something about that before, but we're at the Baker Heart and Diabetes Institute, which is a really nice facility. We focus primarily on cardiorespiratory support devices, so ECMO, bypass and VADs, and pretty much all of our research comes from the clinicians. So the clinicians have their offices just across from our lab, and somebody dies for whatever reason, and they come to us and they say somebody died for this reason, and they say fix this problem. And so we do our best to fix that problem. So our lab's composed of many, many people from many backgrounds. We have professors, doctors, both medical and PhD. We have PhD students currently studying with us, as well as master's students and undergraduate, and we take people and students from both Monash and also internationally. So we currently have many students from Germany, and we have students from France and Italy. So it's a really good and diverse environment. So what did I do in the past? So some of you know about ventricular assist devices already. You know it consists of a drive line, which is that thing there, the controller, which is worn on a belt, and then 2 batteries. And so they're implanted into the heart. They keep the patient alive while they're waiting for transplant or even as a destination therapy, and people can go home and live on these for more than 10 years, which is pretty great for them. So what's the problem then? So the problem is that VADs run at only 1 speed, and the problem is that because the heart is so sick, the VAD is providing most of the support to the body. And as we know, the heart doesn't only have 1 heart rate. When you walk upstairs, it goes up. When you go to sleep, it goes down. So basically what happens with these patients is they can't resume a very good and autonomous life because the VAD does not adapt to their body's needs. So it keeps them alive most of the time, which is great, but there's still some issues with quality of life. So what I do is I look at adjusting the VAD speed automatically based on what the patient needs. So how do I do that? So in the healthy heart, the Starling mechanism describes how much blood the heart pumps out. Basically, the more blood that's returned to the body, returned to the heart from the body, the harder the heart will work to pump it out. So it will beat harder and faster based on what's returned to the heart by the body. So we aim to mimic that in VADs by measuring the pressure in the ventricle just before the heart's about to contract, and then we can speed up or slow down the VAD as necessary to meet whatever the patient needs. So if we look at the Starling mechanism as a mathematical model, we can see here we've got the atrial pressure, so in this case this is the right atrial pressure, and here we've got the cardiac output. And we can see that as atrial pressure goes up, the cardiac output goes up quite steeply up to a certain point, and then it sort of asymptotes off because that's the maximum ability of the heart to output blood. And then what we can also see is this line here shows that in a steady state, the pressure returning to the heart is driven by the right atrial pressure. So what basically this does is by using these 2 lines, you can predict at this point right before the heart contracts how much blood it's going to push out. So that's the native heart, and then we just emulated it for a controller. So all we had to do was we had to measure VAD pressure, we had to measure VAD flow, and then we used the controller return path, which is based on the patient's vascular resistance, compliance, and so on, to predict for any change in preload how much blood the VAD would need to output. So I can show a demonstration of that. So this is the main, this is just a typical resting state, for instance, and you can see the operating point, which is the combination of measured pressure and measured flow. And then, for instance, the guy walks up some stairs, does some exercise, his preload goes up, and then we adjust the venous return line to find a new point of intersection, and then we increase the VAD speed to match that new flow. So that's what I've done in the past. So in such a way we use sensors to facilitate control to improve medical devices. So another part of my PhD was looking at actually developing a sensor. So as you probably know, sensors for the heart are not really that common, especially those for VADs. So I developed a fiber optic pressure sensor that could be used with the VAD, which we could then use to give information to our controller. So the fiber optic pressure sensor used a Bragg grating, which is a periodic diffraction grating, which reflects a specific wavelength of light based on the periodicity of the diffraction grating. So we can see here that because the fiber optic is embedded into a flexible silicon cylinder, it balloons inwards and outwards when there's more or less blood in it. So what happens with the Bragg grating is under positive pressure, the cannula balloons outward, the segments get stretched, and that correlates in a shift in the Bragg wavelength, which is reflected. Similarly, under negative pressure, the balloon squishes in, and we can measure that. So we characterized that sensor, and it was pretty good. And then we looked at integrating it into a VAD. So we've got the sensor here on the pump outlet, which is all fiber optic, and then we've got a fiber optic light source and a conversion unit there, and then the fiber optic light source is powered by the VAD driveline. So pretty nice little device. And then in addition to that, not only have I done direct measurement, but I've also looked at indirect measurement. So some of you might know that the VADs have what they call the flow estimators on them, and basically how the flow estimators work is they look at the speed of the pump, and using the known characteristics of the pump and the power consumption, they can estimate what the flow is. So we did a study to look at just how accurate that was, but not only how accurate it was for the clinical use of VADs, but how accurate it was for off-label use of VADs. So something that happens a lot with people in VADs is they get a VAD put into the left side of their heart, because that's the one that fails first, and then after a little while, the right side of the heart fails too, for reasons that we don't fully understand yet. But we know that it happens. So what clinicians do is they take an LVAD and they put it in the right side of the heart. Now the LVAD's designed to overcome the pressure in the left side of the body, which is all of the organs. And the right side of the heart is only provides blood to the lungs. So when they put the right side, an LVAD into the right side, its characteristics are completely way off. So we looked at using this, how this flow estimator works when the VAD is switched from the left side and the right side. And we found that the flow estimator, when it's used normally, was really, really good. And then when you put it in the right side, it was completely useless. And this was important because, as far as doctors are concerned, this is a sensor. They say, okay, this is the flow. They know there's some error in it, but they may not know exactly how big that error is. So if a doctor is trying to make a medical decision based on this estimator, which is way off, then obviously there's a problem there. So that's a bit about what I've done in the past. Now let's get started. So what is it all about? Why do we need all of this data? So the idea of sensing is about acquiring data to make a clinical decision. So it doesn't matter if it's blood pressure, heart rate, temperature, whatever. It's all data that we use to make a clinical decision. So whether it be, so typically what happens is you've got your patient, you get some signals, even if it's qualitative signals like my throat is sore, you get some data manipulation, so that's filtering, interpretation, whatever. You get some readable output and an expert system. The expert system might be a doctor, it might be some sort of automatic control. So, and then based on that, there's some clinical management of the patient. So it's very much a closed loop circuit. So why do we need sensors? Why do we need direct measurements? Obviously to detect changes in quantities. We normally use sensors to convert one quantity to another. So signals is what it's all about. And so with the signals, they can be temporal, which is 1D with time, or they can be spatial, such as images, which is 2D with or without time. And you can use multiple signals together to get an idea about what's going on. And it's all about decision making. So bad signals can lead to bad decisions. And when it comes to people's health, we don't want any bad decisions. So a bit of the history. So one of the earliest sensors was thought to be the thermostat, which was invented around 1620. And it was completely analog, mechanical. And it used mercury as a feedback system to turn on and off a heat lamp to keep chicken eggs healthy. So if it gets too cold, the mercury drops, turns on the light, heats up, turns it back off. So in terms of biomedical sensors, the earliest sensors were about physical and chemical transduction. So the original blood pressure monitor is this device here. You can see he's physically wearing it on his arm. It's got a little needle there, and as the blood pulse pressure travels down the vein, it draws a little output on this graph here. So completely mechanical. In a similar way, that's how these devices work. Obviously a little bit less obtrusive than that, but still the same thing. So then we moved to the 70s, 80s, back when CRT monitors were a big thing, and they actually, believe it or not, stored patient data on magnetic tapes, or they had to write it down by hand in charts, which is something that we're actually still trying to get away from now. So in the future, in the present, now we've moved to digital monitoring. Everything's stored everywhere. It's online, it's in databases. We're trying to really build that up. And obviously we have all of the fantastic medical devices that we've received in the last 20 years or so. So obviously, back to signals, you've gone over this already. There are all different types of signals. There are signals and there are images as well, and they basically have their own analog. Anything can be used to make a decision. So it's about decision making. What kind of decisions do we make? So oftentimes we look at diagnostics. Monitoring is obviously a huge one. Sometimes it's just about sit and wait. I'm very much interested in automatic control of devices, but that's it's not quite at the forefront of medicine at the moment. Another big area that's coming into play is biometrics and data collection. This is used for both research and epidemiology purposes. People are interested in outcome prediction. If the guy's got high blood pressure and we put him on this medication and his blood pressure doesn't change, is he going to die? This is a huge thing in medical decision making at the moment. And of course research. So we want big data. We want data on all of the patients so we know exactly what's going on with them, what's causing them, and so on. Pattern recognition, which I'll talk about a little bit later, and also epidemiology. So incidence of a disease, what people are these diseases affecting, why are they affecting them, and how can we help them. So interesting to you probably in terms of your next assignment is challenges. What are the challenges in designing a new sensor? So in medicine, sensors come with their own special set of challenges because they're so important, people's lives depend on them, and also the medical environment is very chaotic, especially the sick human body comes with its own really unique set of challenges that you wouldn't get if you were designing a sensor for structural detection, for instance. So one really bad problem in the medical environment is electromagnetic interference. So you've got monitors and imaging devices and all other things out there while your patient's sitting in the ward, and you have to worry about that. How much is that throwing off your sensors' readings? So ionizing radiation is another one. Is your device going to be able to be imaged with X-ray and so on? Regulations, of course, which we'll talk about a little bit more. And then depending on whether you're your sensor is implantable or not, you're probably even going to have even more problems. So biocompatibility, a sick body is a very difficult environment to work in. It's got all sorts of, if you medicate it, it's got chemicals in it, it's attacking everything, it's crazy. So longevity, so will your device be implanted for 5 years? What are you trying to treat? Is it something that's chronic? Is it something that's going to be resolved in 3 weeks? Self and external device heating. One of the problems with implantable sensors is once they're implanted, you can almost never make changes to them. Very difficult to calibrate them, very difficult to change anything mechanically with them. Energy transfer is a big problem if you've got an implantable device. How are you going to keep it powered for the lifetime of the device? Drift is of course one, and also the criticality. So if you've taken the time to put a device in someone, obviously it's important. And if your device fails, what are the issues that are going to happen with that? And actually, a really interesting story on a paper that I read about these sorts of challenges is there was a guy with a pacemaker implanted. He had his heart failure. His family, in a very nice gesture, bought him a massage chair to sit down and relax. He turned on the massage chair and he began to go into ventricular fibrillation because the electromagnetic interference from the massage chair had interfered with his pacemaker. So that's obviously a contingency that the designers of that pacemaker didn't take into account. And it's always very difficult to take into account all of the different contingencies, but as engineers it's our job to do the best that we can. So in addition to the specific challenges, there are some tough design choices that we have to make, and most of you now would be familiar with that as you've been going on with your assignments. Your advisors will be asking you tough questions that you need to decide on. So is your device going to be powered? Is it going to be passive? Is it going to be mechanical? How often is your device going to measure whatever it's supposed to be measuring? How are you going to affix your device to your patient? Is it going to fall off? Is it going to be a problem if it falls off? Is your device an acceptable level of invasiveness? If you want to measure blood pressure, it's probably not acceptable to do a full sternotomy and cut the patient open. But maybe it is. You have to be able to justify these things. How is your device going to communicate? Is it going to communicate? Is it going to communicate securely? This is a big thing that's come in the last 5 to 10 years for devices which want to store data. There was recently a white hat hack to show that people could actually hack certain pacemakers and send different control signals to them. And that's pretty scary. So that's the kind of thing that you need to think about and mitigate. How are you going to take care of your device? What happens if skin starts growing over it while it's implanted in the body? If fatty tissue starts growing over it? How are you going to dispose of your device? Is it going to be medical waste? Is it going to need some sort of special disposal technique? And also, is there a way that you can modularize your device, either to make more money from it or to reduce the complexity of the device? And there are so many more considerations that you have to keep in mind, and all of them are application specific. So when you're designing a device, you should have a very clear application and market in mind, and then tailor your device to meet those specific needs. So I won't talk too much about regulation because Professor Steinseifer covered this in great detail, but I'll just go over it again. By the time your device is ready for clinical trials in people, it's too late to start thinking about regulation. You need to start thinking about regulation as soon as you've identified your market, because especially with the FDA and the TGA, every single change you make to your device, you need to be able to justify and then show that that change was an improvement. So if you've only just started to think about regulation by the time your device is ready, it's too late. So in Australia, we have the TGA Australia. There's actually a really good online policy bank there, which is great for documentation on Australian, New Zealand medical device approval. It's a bit of a shame that you've all now handed in your assignment too, because that probably would have come in handy, but anyway, it may yet be of use to you. So the peak body is the FDA in the USA, the CE in the European Union, and the Chinese FDA in China. All of the different countries have their own peak bodies. There's been some work in recent years to try and get a coalition of medical regulatory authorities to sort of globalize and streamline the approval of medical devices and medical therapies. So far there are many member organizations, but it doesn't quite have the authority to that it sort of is seeking for. So tools for regulation is the biggest nightmare of all, which is ISO. So we use standards to help get our devices approved through the regulatory bodies. Now, if you've ever looked up an ISO document, they're an absolute nightmare. They have standards on how to write standards. It's ridiculous. They're basically unintelligible, but these are all things that you have to adhere to in order to get your device across the line. So within ISO, there is an Australian branch called Standards Australia. So looking at translatability, you've gone through the market, you've put your device. What happens if your device fails? So what happens if you think you've done everything right, you've followed all the regulations, you've followed all of the standards, and your device directly or through negligence kills somebody? And I'm not talking about who gets sued, because it's probably the company that gets sued, but how would you feel if you engineered a device and it killed someone because you made a mistake, because you weren't thorough enough? Who's to blame? Is it you? Is it your supervisor? Is it the company? I don't know the answer to that. Personally, I've seen people face this dilemma whereby their devices were ready to go to market, and they were ready for clinical trials, and they were tossing and turning in their sleep. What if this kills somebody? What if I'm responsible for killing somebody? Or, you know, so that's just something you need to think about when you're designing your device, and hopefully some inspiration to do a good job. So we'll look at a few very brief case studies of direct measurement in medical devices. So I think one of the best examples of this is the insulin pump. So some people might have seen this already. Earliest approval was 2003 in the UK, and what it does is it releases small amounts of insulin throughout the day to regulate the insulin, and then to regulate the blood sugar, and then if it detects a large drop or rise in blood sugar levels, it will administer a large bolus then. So I think the really good thing about this is one of the very few instances where feedback control from sensors has been implemented clinically. So this is actually a sensor, and people trust what it's saying to do, to allow the device to work autonomously, and it works incredibly well. So one study, a series of studies showed that by having this automatic feedback device, insulin injections were reduced by 90%, kidney damage by 51%, nerve damage 41%, eye damage 53%. Obviously, and these were in prospective randomized trials, obviously these trials were conducted by Medtronic, who have a stake in this, but regardless of how biased the science is, a 51% reduction in kidney damage, 41% in cardiovascular and nerve damage, and 53% in eye damage is a huge reduction. So I really love this example because it shows just how useful automatic control of devices can be and how it can genuinely improve patient lives. So how it works is there's a little sensor patch which goes on the arm or on the hip or wherever, and it wirelessly sends information back to the control unit, which has a little it's got a little insulin bolus in here which can be exchanged, and then it's got a little injection site. as well. And so the patch detects the the glucose levels in the cells, in the superficial cells there, and then it just in real time monitors the blood sugar. Obviously, there's a bit of a lag between when there's an insulin injection and when the blood sugar changes, because it's got to go through quite a complex metabolic system, but it's really cool. So this patch gets changed out once a week, twice a week, once every 2 weeks, depends how dirty you are. And then now patients don't have to do their pinprick, check their blood sugar level, take the insulin, not take the insulin. So I think it's a really cool device, a really cool application of sensing to devices. So another case study which Sean touched on is the CardioMEMS. Now, the thing that I like the most about this device is that it's completely passive. It has no active components at all, which is amazing. The first time I saw this during my PhD, it absolutely changed my way of thinking on how sensors could be made. So you might remember that this contains a flexible membrane with a capacitor, which is in contact with the blood in the right atrium, and it also contains an inductor and some resistance. And we know that capacitor, inductor and resistance gives a resonant frequency based on the values of the RLC components. So when the flexible membrane changes the capacitance, we can see a change in the resonant frequency, which is then correlated to a change in the blood pressure. So this is a really amazing thing. What happens is they insert it minimally invasively, which is already amazing. It doesn't require a surgery. It goes in an introducer and a sheath, and they stick it into the neck or the groin. They introduce it up into the pulmonary artery, and then they pull it back and it pops open like a balloon, which is already an amazing feature. And so it sits in the pulmonary artery where it's in contact with blood, and the membrane moves in and out, and then you use a little RF wand outside of the body over the pulmonary artery, and it reads out the blood pressure based on the resonant frequency. So that blood pressure is measured, it gets stored, it gets sent to the cloud, the doctor goes and downloads it the next day. He can see how his patient's blood pressure is going long term while the patient's at home. It's really quite a nice little device. An interesting thing is why the pulmonary artery. So this device actually has a pretty nice little story. They tried to get it approved for the left atrium, which is actually significantly more useful to measure, in my opinion anyway, and it didn't get FDA approval because it didn't show improved outcomes compared to the current gold standard. So it didn't hurt anyone, but the FDA would not approve it because it didn't make anyone's life better. So that's a really interesting sort of point to think on, that even though your device works perfectly, the regulation is very strict, and you actually need to show that it does something useful for them to be able to accept you then implanting it in people or using it on people. So they did show an improvement in patient rehospitalization while it was implanted in the pulmonary artery, so it was approved for that purpose, but it can't be used in the LA. So another case study, which is experimental, this isn't something that's been clinically used, but I also think this is really cool. It's a fiber optic that they're using to detect either DNA or antibodies. So what they do is they put a completely bare fiber into the bloodstream, ideally, and you may remember from your first year physics that Snell's law about the law of refraction. So refraction is dependent on the interface of the two mediums. So the refraction of light is dependent on the density difference between the interface of the two mediums. So what they do is they put a bare fiber into the bloodstream. They put a special coating on it which catches DNA, and then the more DNA it catches, the more the wavelength of light shifts. So in that way, they can actually see how much DNA is growing on the fiber. They've also done this for antibodies. So what they'll do is they'll coat the fiber in an antigen, which antibodies then attack, and then they can measure the number of antibodies in the bloodstream by how many attack this fiber and how much the reflected wavelength changes. So I think this is a really cool example because it's using this technology in quite an unexpected way. This is not something that we've seen a lot of previously, and it really sort of emphasizes that there are many different applications that we just have not thought of. So don't fret, there's always something to be found and there's always something to be solved. So that's the sort of first half of the lecture. Are there any questions on that so far? Nope, pretty shy. Okay, let's carry on. Indirect measurement. So what the hell is indirect measurement? So when we're talking about indirect measurement, we're talking about sort of two different schools, but they're kind of different, but they're also kind of related. So we're talking about estimation and pattern recognition. So what's estimation? We all know what estimation is. It's an observation which is incomplete, which we can use to make some sort of guess. It can be an inference, so a correlation with or without a causality between two metrics, and it's an approximation as well. So within this sort of estimation, pattern recognition in indirect measurement, we've got, of course, pattern recognition. So pattern recognition is actually a basic biological function that we've adapted to electronic systems. So the body knows when there's foreign cells inside the bloodstream and it's able to attack them. That's pattern recognition. As I'm talking to you, sound waves are traveling through the air, they're hitting your eardrum, and you're able to recognize patterns to understand what I'm saying. We've adapted this pattern recognition to artificial systems so that we can detect usually very complex phenomenon with a whole series of random data. So within pattern recognition, a huge part is feature extraction, in which you want to identify important patterns and classify them. And also you want to use pattern recognition for prediction and decision making as well. As with our direct measurement, it's all about decision making. So signal processing. Signal processing is obviously important for both indirect and direct measurement, but it's way, way, way bigger in indirect measurement. So signal processing is what we do to take raw data and augment it so we can use it more easily. So signal processing can include filtering, smoothing, sharpening, reducing noise, amplifying your signal, convolution, which you should be familiar with, digitizing, so taking a continuous signal and digitizing it for electronic purposes, mixing and superposition of various signals, transforms, of which I'm sure you know a few, and so on. So within indirect management, signal processing is probably the most important step, because the better quality signals you get, the easier it's going to be for your system to do its job. So implementation of indirect measurement. The problem with indirect measurement is you pretty much have to know exactly what you're looking for. The reason for this is usually your system will require a large amount of training data to be able to categorize and identify a specific event that you're interested in. So, for instance, one of my lecturers back at university was a pretty keen guy on machine vision, so using machine vision for various things. So what they were asked to do is they were asked to develop a machine vision system that could detect violence occurring in elevators. So they made this incredibly robust system, so they thought, where if somebody was about to hit somebody, punch somebody, any sudden movements, that the system would identify that and send an alarm to security to know that there was violence going on in the elevator. So they deployed this system in the hotel or wherever it was that they deployed it, and about a month later, the people who asked them to develop the system came back and they said, look, there's a problem with your system. It's constantly going off with false positives. And they said, what's the problem? So the system couldn't identify the difference between somebody being attacked in an elevator and people kissing in the elevator. And so they were constantly getting false positives. And so I think that's a really good example of why indirect measurement can be so powerful. It can detect all of these different events, but then in the end, it came up with an event that it didn't know, and it didn't know how to deal with it. So I think that really highlights sort of the advantage and disadvantage of indirect measurement. So again, it usually requires a huge amount of training data, hundreds of gigabytes, depending on what you're trying to detect, how complex it is. The more you need it to do, the more computationally intensive it needs to be, and the more complex your system will be. That's obviously a trade-off that you always need to consider. So the system will work within specific boundaries, and usually it will do quite well what you ask it to do and what you've trained it to do, but if it encounters something unexpected, it is going to behave in an unexpected way, guaranteed. So we've found our indirect measurement. How do we apply it? So in terms of estimation is really useful in places where it's very difficult or impossible to measure something directly. So the VAD flow estimator is a great example, because we can measure flow for VADs. There are sensors out there which exist, but it adds complexity and it adds danger to the patient, and the risks, according to the manufacturers of VADs, are not worth the information that we get out of it. So they use estimators. One of the fantastic things about estimators is that you can use one or many parameters to detect one or many parameters. So as long as there is some correlation, you can detect something else. So a colleague of mine told me that there is a correlation between how many people drown and how many people eat ice cream on any given day. That's ridiculous. There's obviously no causation there, but the fact is, when it's hot, people go swimming and people eat ice cream. The two are indirectly connected, and therefore we can use the number of people eating ice cream to estimate the number of drownings. So that sort of gives you an idea on the power of estimation and how robust it can be. So pattern recognition, again, you can use one or many variables to detect incredibly sophisticated events. It's becoming huge in biometrics and hemodynamic monitoring for either identifying risk factors, looking at patient outcomes and predicting patient outcomes, and also identifying where disease is going to occur, how it's spreading, and so on. And pattern recognition is obviously huge in computer vision and medical imaging, so the big medical imaging companies are all developing various pattern recognition softwares to do various things, find out how bad your aortic aneurysm is, all sorts of things. So regulation and liability. Ideally, a perfect estimator should be indistinguishable from a sensor. So you basically want it to be as good as a sensor in order to put it into people. I would anyway. So regulation and liability on indirect measurement is a lot less clear, and that's because there's not a lot of it in the medical industry. I think it's probably obvious why there's not a lot of it in the medical industry, and that's because reliability. So one thing to think of outside of medical regulation is, outside of official regulation is a doctor going to use it? Because the doctor's ultimately the one who's open for liability if he kills a patient, because he's decided to use a device. And so a lot of doctors won't use something that they don't completely understand. It takes, to get a medical device not only to market, but from market and into hospitals where doctors are using it routinely, normally takes one or two really well-respected and brave doctors to take that first leap and go, yes, I will use this in my patients, and then others go, okay, he's had good outcomes, I'm willing to take that risk. So if you make a really complex estimator or control system and you can't explain it to a doctor in terms he'll understand, I can almost guarantee you he won't use it. An interesting point about an estimator with regards to liability is an estimator is much less likely to fail outright. So with a sensor, if your sensor dies for whatever reason, then you're going to have a critical failure. Estimators, generally the way that they're set up, they don't fail outright in such a way. So that can be a sort of bonus to that, although they are more likely to give errors. So a very brief case study on flow estimators, So I talked a bit earlier about the VAD flow estimator. So it's very inconvenient to place a sensor on in the VADs because it endangers the patient. It's actually relatively simple to estimate VAD flow as a function of speed and power, as some of you have looked into for your assignments. And it usually works really well for the typical VAD patient. So we showed that it does work well for LVADs, doesn't work well for RVADs. The interesting thing about this, though, is it's not actually marketed as an estimator. So nowhere on this console, when you're reading out 5.4 litres a minute and you're looking at this flow waveform, does it say estimator. So a very ignorant clinician could take this as fact rather than an estimation, which is a really interesting sort of marketing strategy. So as engineers, we know that it's an estimation, but it's probably not that clear to clinicians. I'm sure they have a disclaimer somewhere in the manual which says this is only an estimation, but who reads the manual? So another really awesome, case study is brain-computer interface. So this is really cool. What they do is they get this bracelet with a bunch of sensors on it, and they place it on the wrist, and then they use nervous impulses while the person's moving their wrist to train the device and capture data. So the transformed data is then classified by feature extraction pattern recognition to try and say what the person is doing with their hand. So there aren't a lot of clinical uses in medicine, but I will show you just some awesome applications. Oh, yes, I have to click on this one. Idiot.
We're able to actually decode just from the nerve itself what the hand is doing and create a biologically accurate hand virtually. All the fine digit movements, flexions and extensions. This is a hard problem. And I think it's impressive. What you'll see next is how we actually do something more complicated. What you're seeing here is my intention. I'm not moving, but the nerve is active. And I'm just trying to wave my hand back and forth without moving. Here I'm showing the forces that I'm able to generate. This is just a simple grasp. And I actually have nice control over this. I could probably generate a number accurately between about 0 and 200. We're imagining what it's like now to take your hand virtually into VR. There's no cameras involved here. This is an always available you. Of course, the problem you're going to want to solve next is textual interactions, not just these sort of interactions that would be broadly based on moving your hands around. And this is work we did last fall. It's quite a bit further now, but this is me trying to type with some amount of spell correction, just kind of typing in the air. You'll see the device pop up on my arm here, and this is all your interface belong to us. And this is the future. It gets crazier. I want to show you neurocontrol. So neurocontrol is no longer about you moving, it's about you not moving. This is my co-founder Patrick Kaifosh playing Asteroids on a phone. Asteroids in the arcade took 2 hands. I wish we had the sound on right now because it's actually kind of fun, but the point is he has incredibly fine continuous control over asteroids, 2.5 degrees of freedom. Very fine control out of 1 hand, and he's not moving at all. You'll have to take my word for it. There's a device on his arm there. And what's crazy is he can train this in less than 60 seconds. De novo training. So this is continuous married to discrete degrees of freedom. Further, this is one of our lead scientists, Adam, who's going to show you how we map this to crazy things like a 7 degree of freedom arm. He's going to do some slight motions, which he's mapped to certain things, and then other things are based on things that are happening in an ulnar muscle, a residual from the ulnar nerve. And he's controlling this thing that you couldn't actually just map to your arm. It's got a wrist that can go 360 degrees. You would never be able to do that. All right. I want you to imagine where we see this going along with me. So yeah, you can play with 7 degree of freedom arms, but there's no reason why this wouldn't become the default interface for all of your interactions in the world. Finally, you can stop correcting the autocorrector. Just look at your phone and use it as the output device, which is really all it's good for anyways, and type on it, or do any kind of interaction. Play Asteroids. Don't swipe on it. We imagine this device being something that's always on and always available for you. It's the universal controller, or rather you are the universal controller.
So the rest is just a bit of advertising stuff. But what? Like, seriously? That is amazing to me, I think. So he's got that thing there. He's training it as he goes. So he does the initial training. He holds it closed. The thing does what he thinks on the screen. It's incredible. I think, anyway. So that is sort of an idea of the most sort of highest level of all of this sensing and estimation. Obviously, there are dozens and dozens of applications for this in medicine. So paraplegics, people recovering from strokes, so on and so forth. I just think this is just the most amazing thing I've ever seen. So we'll look a little bit about how these types of brain-computer interfaces work from a signal processing point of view. So in this case, we're not using impulses from the wrist, but very standard EEG probes that are embedded in a very stylish cap. So
I'm back in to show a simpler BCI compared to what I showed in the last video. If you haven't seen the last video, I would recommend watching that first because I explain what I'm doing, what my project was, BCI being brain-computer interface. And in this video I'll be going through stuff based on that, so I'd recommend watching that first. So because I didn't have a functioning BCI in the last video, I wanted to do kind of a proof of concept that the circuit can be used for a brain-computer interface. So the way I'm doing that is by monitoring alpha waves. So this time I'm connected to 01 and 02 according to the 1020 system for my 2 measurement electrodes, and then I have the driven relay connected here. I'm using 01 and 02 rather than OZ and the left mastoid compared to the last video, as from my experience I've been able to get better results measuring alpha waves using 01 and 02 compared to OZ and right or left mastoid. So yeah, that's why I'm connected up that way. So I'm just going to show you a trace of what I'm measuring now. So on the top there you'll see the real-time trace of what I'm measuring between 01 and 02. So a lot of activity, but I can't tell you exactly what's what. And down on the bottom we can see an FFT of every second of the real-time trace. So I'm going to close my eyes and hopefully you'll see the 10 Hz spike that we've seen before. And so I'm going to do that now.
So if you don't know how to read an FFT, there's a spike,
So yeah, I just opened my eyes and I
Around
did see there
there.
was the 10 Hz spike that
which you can see
before.
quite clearly.
So that spike is going to be used to control a simpler BCI, which I'll show now. I'll just set up now and start recording again. So I'm back now without the swim cap this time, but a bit of hair sticking up because of it. But anyway, I pre-recorded me using half-wave BCI because I wasn't able to get a reliable trace while I was moving around and talking, and I need to get a good baseline for calculating threshold for the alpha wave so I can improve the alpha wave detection. So I'm just going to do, I'm going to talk over video recorded. So I'm going to start that now. So for the first 30 seconds I'm going to be recording the baseline to calculate that threshold, as I said. So I'm just going to be staring into the centre of the screen, not moving around and not moving my eyes or blinking or doing anything really. And then when it's done, you'll see this no box gets bigger. So my eyes are open, so I'm using that as a no. So when there's no alpha waves, that's a no. So whenever I close my eyes, the S box should get bigger. So my eyes are closed now. The S did get bigger there, but it's not constantly bigger. The second time I try and close my eyes, it does work a bit more reliable. But you do see the yes does get bigger a lot more often than when my eyes are closed and when it's open.
So that's sort of a little bit of a show on what you can actually do with this. So what he does is he takes two very, very easy to get electrodes and he puts them in his cap. He gets all of the output from those electrodes and he runs them through a very simple FFT, and then he is able to use that to determine between opening and closing his eyes. Now this is not some sort of amazing science guy. As far as I can tell, this is some nerd with a Raspberry Pi and a couple of off-the-shelf EEG monitors. That's how easy it is to get started on this thing. And there are actually huge open source libraries on how to do these sorts of things with Raspberry Pi with Arduino. So, I mean, if this is something you were interested in, you could start doing this today for under $50. So that just shows how simple these things are in reality, but the complexity of building up to that's so amazing. So before we go into the summary, does anyone have any questions so far? No, still shy. Okay. So a summary. So which is better, direct or indirect measurement? Direct measurement, what's good about direct measurement? We know it's accurate, ideally. I mean, you designed it, so it should be accurate. It's robust, it can handle a bunch of different situations. It doesn't care about anything else going on around it except for exactly what it's measuring. They're simple. I mean, most of these sensing solutions are incredibly simple. They take one signal, they convert it to an electronic readable output, and you're able to find out what's going on, whatever you're trying to measure. Sensors are well established, they're well known, everyone sort of knows what it is, doctors can trust them. Oh yeah, it's a pressure sensor, I know what a pressure sensor is. That's all good things about direct measurement. What's not so good about them? Hardware is generally way, way more expensive to develop and to manufacture than software. They are prone to critical failure. So I can't tell you how many times I've been in the ICU and we've had a blood pressure monitor on the patient, and then something grows over the interface of the monitor of the sensor, and it just stops working. We have to switch out the pressure sensor. It happens all the time. If you've got a device that is relying on this for some sort of feedback and it fails, then what's your feedback mechanism going to do? You've got to be able to answer that question. And obviously, it's a little more rigid. So a sensor is designed to do one thing, usually. It's designed to transduce from one signal to something else. So what's good about indirect measurement? It's cheap. Almost all indirect measurement is some very rudimentary signal feeding back into some very complex software. Software is always cheaper to develop than hardware. It's versatile, so we've seen it can detect so many different and interesting and complex things. And you can theoretically measure anything with a correlation. I mean, that's amazing. There doesn't have to be any causality whatever. As long as there's a robust correlation, you can measure anything. And also, they're less subject to critical failure. But on the flip side, they have higher range of error. So what's bad about indirect measurement? They're highly specific. So we talked about how they are only able to deal with certain events, and then when something unexpected comes along, they can't deal with it. They are usually very complex, almost to a fault, and the doctors may or may not be interested in adapting them clinically. They're not really that well understood in terms of regulation and liability. And also, even an estimator is going to require high-quality inputs from somewhere. So, for instance, going back to our flow estimator example that we're leaning on very heavily, if the power load going to that estimator, if the signal going to that estimator reporting on what the power is not correct, how is it going to affect your estimation? I can tell you the answer for that. So the way that the HVAD calculates power, for example, is it looks at the back EMF across the resistance of the driveline, which is a known resistance. When we get the VADs that are explanted from patients, we repair them so that we can use them in research. And to repair, because when they take the VADs out of the patient, they cut the driveline in half so that they don't pull the infected part of the driveline back through the patient. So they pull the infected part out and then they take the VAD out via their median stenotomy. So what we then do is we repair those cables with some just regular copper cable. So when we then did that HVAD flow estimator study, and we used the devices with the copper cable, the repaired devices with the copper cables, the estimator was constantly reading above 10 litres per minute, which is the maximum that it can read. The reason for that was we changed the resistance of the cable, which changed the calculation, which then changed the output. So even estimators require some sort of high quality input from somewhere. Normally it's a lot simpler than what a sensor requires, or what a sensor does. The input is usually a lot simpler than if it were a sensor, but it still goes to show that estimators they still rely on some signal from somewhere. So which one is ultimately better? Who thinks direct measurement's better? Yeah, one guy. One guy thinks direct measurement's better. Two guys. Okay, who thinks indirect measurement is better? About 5 guys. So the reality is they're not mutually exclusive. One is not better than the other, and we can actually use both to make really robust systems that can do good things for our patients. So especially coming back to this thing about the clinicians, they tend to distrust new technologies. The more redundancies you can put in place, the better that people will trust them, the better that you can sleep at night. So this is especially true in the realm of automated control. As far as I know, for instance, the insulin pump doesn't have anything in place for if the sensor critically fails. Now, in this case, the sensor is so basic that it hasn't happened yet. It's a very similar technology to the CardioMEMS RF technology. But it's always good to have a little bit of redundancy, especially in automated control where a failure could be fatal. So what's the future outlook? So in 1966, the medical tricorder was imagined, and it was imagined as the ultimate diagnostic tool. It can take all of the vital signs, it can scan, it can tell you exactly what diseases you have, how much radiation you have, and diagnose anything. And it was handheld. Does anyone know about the medical tricorder? Does anyone know where this is from? No. Okay. You guys are terrible nerds. So this was in Star Trek, imagined by 2323. So we've got a few years to go yet. Very interestingly, there are competitions out there with $1 million prize pools to invent the best tricorder. So this is something that they're actually looking at in the healthcare system, in medical research. They actually want an all-in-one, it's the ultimate goal. It's the ultimate goal to have an all-in-one hemodynamic, physiological, scanning and imaging device that can diagnose patients. So they have this big competition in America, and the winner is the person that can successfully cram the most diagnostic devices into a handheld. And it's worth $1 million, so yeah, why not? So that's the future outlook from 1996. This is from a paper in 1999. Now this paper here was written in the Census, was called Census in Medicine, and is in the British Medical Journal. That is actually one of the oldest medical journals in the world and is very well respected. So as I'm telling you this, just keep in mind this is not some unindexed paper. This was actually published in a really good journal. So in 10 years' time, they predicted that the vent on the ceiling of the lobby will be an air monitor which detects and reports any visitor who might transmit an airborne infection to a patient. As far as I know, we don't have that, but it's a very generous prediction. So the bacteriology lab will be replaced by handheld biosensors functioning as electronic noses and characterizing organisms in urine and other bodily secretions. So I don't think we quite have that there yet. A diabetic patient will have no diabetes-related problem, seeing as a smart glucose sensor or insulin reservoir will be planted. Well, they got that right, but to be fair, they only looked ahead 4 years in the future for that one, so give or take. A physician or nurse will obtain information online about a patient's blood chemistries, ECG, blood pressure and temperature. Well, actually, that's really sort of becoming quite true. That's a huge step in the current medical landscape. It's all about having as much data, patient data online for all of the reasons I've mentioned before. So this was what is expected in 1999. He got a few things wrong. He got a few things right. The take home is don't underestimate how slowly science, and particularly medical science, move. So, I mean, the top two seem relatively bizarre even by today's standards 20 years later. So, the future outlook now. This is a paper which was not published in such a good journal, but somebody still published it. It is a toilet of the future, and it measures weight, heart rate, temperature, bioimpedance, patient ID. I assume that means they have some sort of RFID device either in their butt or in their pants. I don't know how it measures patient ID. Maybe it's a cheek scan, who knows. And also urine analysis. So I'd like to direct you to some of the sensors in there. It's got a scales for weight. It's got some sort of thermal temperature there. These are bioimpedance sensors which can measure your bioimpedance, very useful. It can measure your heart rate. I'll let you imagine how it does that. And urine parameters. I'd just like to point out, this is a camera right there. Yeah, I don't know if I'd use that toilet, maybe. Might end up on the internet in one of those dodgy sites. So I also would like to direct your attention to this fine graphic, which is possibly the best graphic I've ever seen in a paper. It's like one of those scary Shrek meme things. The look on that woman's face is just horrific. So that's the future outlook now. The future is now. But on a more serious note, of course, what are people interested in now? So medicine now, and sensors can help to achieve this is all about personalization. Everyone wants a specific treatment that is specific to them and that they have control over. So one way that people are looking at that is online care delivery and telemedicine. People want to get treatment on their terms when it's convenient to them. They want online information specific to their needs, to their disease. So gone are the days where people implicitly trusted whatever a doctor told them. Now people, they go to the doctors, they've done their research, they know the pros and cons of a treatment, they know the potential side effects, and they want the ability to choose their own treatment. And that's a huge thing that we can deliver with various sensors. They want control over their own treatment, and they want to be able to monitor their own vital signs. Now, this is possibly a good thing and a bad thing, because if you're constantly looking at your blood pressure and you notice it going up, and then you get worried about it going up, you get what's sort of like a white hat hypertension, a white coat hypertension. So there is potential for this to be misused, especially for hypochondriacs. I'm a bit of a hypochondriac, you know, so I can understand why people are like this. One really just fundamental thing that I don't know how the Australian government's going with now, but permanent electronic health records. It seems like it's just such a basic thing, but no one's been able to do it right. Every time I go to a new doctor, I have to tell him my whole family history, which, by the way, I can never remember in total. And it's just ridiculous that we don't have these electronic health records that follow us around. I understand there are some privacy problems there, which we'll talk about in a bit, but this just seems like such a basic thing. So these are some of the personalization aspects that we're looking at going forward in the future, and that sensors can really help us to deliver on. So online connectivity. This is a really interesting point. So I recently went to a biomedical conference in Hawaii last year, humble brag, and that the university paid for. And so they had a company there called Verily. Now, I didn't know this at the time, but Verily is the biomedical engineering wing of Google. So what they were proposing to do, Verily, and they made it sound all very positive, is they wanted to have these smart contacts that you could wear that would measure biological markers. Now, they didn't say what biological markers they were going to measure, because it was a bit of a marketing thing, but the whole time I was sitting there thinking, I don't want Google knowing my biological markers. Like, if I look up something shopping for the next 6 months, it comes up on my phone reminding me to buy it. We know that large-scale companies like this have abused our data in the past. Are we willing to allow them to collect this data, even if it benefits us at the cost of our own privacy? I mean, that's something that you can think about. Personally, it's something that I think bothers me, and especially going into the future, I wouldn't necessarily want this. But then, at the same time, should personal privacy impede social and research changes? So if we had the complete disease and hemodynamic history of every single person in Australia, imagine the amount of research we could do, and imagine how quickly that would accelerate research and therefore benefit society. Is your personal privacy worth impeding research, worth slowing down research by 50 years? I don't know the answer to that. And I don't know who has to decide that. But also sociological changes. If we can detect disease outbreaks more quickly, because we don't have to wait for people to get to end-stage symptoms to be diagnosed. For instance, measles. Every time there's a measles outbreak, if we could tell that someone has measles immediately, we could quarantine them and potentially stop other people from getting it. So, I mean, that's why we have vaccinations, but you get the point. So, is your personal privacy worth holding up the advancement of human health? I don't know. I don't know who should regulate that either. How far ahead must we look? We've got a great example is the internet. Nobody expected it to be this influential on our life, and now we don't know what to do with it. We don't know how to regulate it. Should it be regulated at all? Should it just be let loose to run free? We don't know. The same thing is going to happen with health, especially as we start to collect data on people, personal data on people. Who has to regulate it? What is it acceptable to share? Who should decide what it's acceptable to share? Should we have an opt-in system? I want to share my blood pressure every day. Or should we have an opt-out system? I don't know. That's something that we'll have to solve together in the coming years. And also, what boundaries are we willing to cross? So at the moment, we can put artificial hearts in people and keep them alive for 10 years. That's great. What if they need artificial legs? What if they need artificial arms? At what point does a person stop becoming a person and is just a machine, just a head in a jar? Is that okay? I don't know. So these are things that we have to genuinely consider because they're not that far around the corner, although we should not underestimate the slow-moving nature of science. So a more succinct summary. Direct measurement. It's all about signals, though. It's all about signals. Usually 1D, usually temporal, not always. There are just a myriad of technologies out there already, and there's more to discover. I'm sure somebody can discover something new. Each sensor must be designed for a clear application at the outset. It's no good saying, yeah, I want to detect blood pressure. Where do you want to detect blood pressure? Who do you want to detect blood pressure in? What are you going to do with that information? These are things that are really interesting. Think on standards and regulations early, because these will affect the development of your device. And it's all about decision making. So bad signals will lead to bad decisions and somebody will get hurt. Indirect measurement, it's still all about signals. 1D can be temporal or spatial. Oftentimes these things are spatial. Are spatial. There's huge growth in this sector. If you want to get into this kind of thing, now is the time. It is gangbusters at the moment, particularly in the computer vision thing, but also you saw with those brain-computer interfaces, they're blowing up right now. So the estimator must be as robust as possible for all contingencies. You just have to do your best as an engineer to identify as many things that can go wrong. Still think on standards early, as they will still affect your development, and weigh your opportunities when thinking of between indirect and direct measurement, because remember they're not mutually exclusive, and redundancy can be weighed up against complexity and the criticality of the application which you're using. So I'll do a very quick plug for my lab, which is a great lab. We have lots of final year project opportunities, summer internship. I would highly encourage some of you to come and join us for that. We have controls on device control, automatic device control, sensing, device design. We have more patient-focused, patient-orientated projects. We have designs in optimizing design. We have projects in optimizing design and optimizing various technological aspects of whatever we're working on. I can guarantee you a HD. I was hoping the website, if you come do it with us, I was hoping the website would be up. Monash is giving us a bit of trouble with that. So we take final year projects, interns, masters, if any of you are interested in doing masters by research, and also PhDs. It's a wonderful life for PhD. Actually, it's pretty awful, but there are some cool perks. You get to travel around a lot on the university's dime. You get to wake up at 10 o'clock in the morning and go to work at 11. It's great. So, yes, that is all I have to say. Thank you very much. And do we have any questions? Nobody has any questions. I thought I covered some really interesting stuff there, but nobody has any questions about any of it. That must be... Yeah.
Was that EMG sensors?
What's that?
Were those just EMG sensors?
I'm not sure what sensors they were using. I just saw it on the internet and I was like, wow, that's awesome. I'm going to put that in my lecture. It's crazy stuff. Yeah, so, oh well, I guess if you guys are a bit shy, feel free, we've got a little bit of time. It ran a bit longer in my practice run, so I must have forgotten to say something. If you guys have any questions, you can come up to me after class. If you want to join the lab, I can give you my card if you're interested in signing up for an internship. Otherwise, I hope this is helpful in designing your sensor for your assignment. Thank you.
Really good lecture.
Thank you.
I'll see you next week. I'm back at the lab.
Okay, no worries.
That was really good.
Thanks. Was all right.
Yeah, definitely.
Wasn't too boring. I thought, yeah, the guys at the lab seemed to like it. So
Helps from the content itself is interesting.
yeah,
This is the fun part of engineering.
yeah. I thought I didn't know if Sean would be happy because it's a bit like content light. It was more just to like inspire you, get you thinking about stuff, whatever. I don't know. Guest lecture's not supposed to be taken seriously. Right? It's just a bit of fun.
Could I be able to grab a card off you? It'd be interesting.
Of course. Yeah, definitely. Hopefully I brought enough. So, that's me. That's me. I didn't.
When do you run internship programs?
So the internship, they have it's through Monash. So there's a Monash, it's called Research Experience Program or something like that. It's a 10 credit point course, I think, and we do it over summer for 3 months. The students that did it last semester loved it, and they even still come back in their own time. That's how much they love it, to come visit us. So you'll get a small project. 2 of the projects that we gave out over the last summer internship will eventually be turned into papers. So you can actually get some really good output from it. Same for our final year projects. We offer them every single semester. Yeah. Cool. So you'll have to go. So for the internship, I don't know when you apply for it. I just get emails from Monash saying, "Do you want to take this student?" And normally we go through an interview, like a fairly informal interview process, talk about what kind of project you'd be suited to. And then Monash just send us a thing and we go, yep, and then they're signed up. So you would have to talk to whoever coordinates the student final year projects would know, I guess.
Oh, okay, cool.
I don't know.
Yeah.
All right.
All right, see you.
Thanks.
See you there.
All right. Hi, guys.
We're speaking about how the manufacturers, even though they could implement, flow sensors into the EAD, but they didn't. Like, can you be more elaborate?
So every time the manufacturers have to make a change to their device, they have to go through FDA approval. So what they could do is they could put the flow sensors on the device, and one device does have the flow sensors. It's called the AVAD. It's by Reliant Heart. It's not used very commonly clinically. So they weigh up the fact of what extra are we going to get out of putting this sensor on, and how much extra complexity is going to add, and what risks does it pose to the patient, and how much is it going to get to push us back to market with this sensor on. And they go, we're not going to make enough money out of this, and we're not going to save more lives or get a better reputation by implementing this than from the current setup that we have. And the other thing about VADs specifically, and a lot of medical devices, is there are like 2 or 3 big companies that have 90% of the market share, and so they have sort of a mutual agreement not to one-up each other, so that once their devices get pushed to market, they can just go, all right, we're just going to leave it like this for 20 years. And that's exactly what they do, until enough people start saying, we want this, And enough research shows that this is the benefit that it's actually worth them in financial dollars to make these changes. So that is one of the reasons why VADs don't have flow sensors.
But like if we decide to implement flow sensors into LV8, do these big companies like pose a threat to us, or like will they?
So what the big companies normally do is they will go to the conferences. They'll suss out all of the under development devices, and they'll go, is this thing close enough to market to be a threat to us? And then as soon as it gets close enough to market to be a threat to them, they buy it and they put it on a shelf. And that's it. That's exactly how it works. It's happened to at least 4 different devices, VAD devices that I know of. Big companies bought them out because, I mean, when you're building a device, it's a hard slog. Any startup is a hard slog, but specifically a medical device startup, you've got to work long hours for almost no pay, and then by the time somebody comes along and says, here's $100 million, you're like, thank you, I'm going to retire. So some people are passionate enough to see it through, but it's a much longer road than just getting bought out. And being bought out is an acceptable way of doing business, okay? You don't feel bad about selling out, okay? I mean, especially if you genuinely think the company's going to take your device and get it into people sooner, it's not a dirty thing to do. And a lot of times, that's how translation works. I used to think that translation was, I have an idea for a device, and I develop it, and I'm sitting by the patient the first time it gets put in, and he wakes up and he thanks me. It's not always the reality. The reality is selling your idea to a company who has billions of dollars and can do it faster is a genuine way of still making a device that helps people, and you get to make some money on the side. Probably better money than if you tried to market the device yourself. Okay? Thanks, guys. Hi.
I'm quite interested with the lab you just mentioned.
You want to visit the lab?
Yeah, I'm interested with that. Is it available for international students?
Of course.
Okay.
Of course. So are you here, are you a transfer student?
No, just an international student.
Okay, so are you going to do the rest of your degree here, or final year project? Yeah, definitely, we can definitely take international students.
So it's a summer internship?
So we've got summer internships between, I think it must be November and February, and then also we do final year projects. Yeah.
I will go have a
Email me.
Thank you.
Thank you.
Can I have
Yes.
just along the same lines? I would also like to visit the lab if possible.
Are you guys friends? I've only got one card left.
Yeah, sure.
You guys can reach me at my Monash email. This is my research email. So you guys,
Sure.
you've got my email.
I think
I'm supervising you anyway. So yeah. Thanks, guys.
What's the process for the internship in summer? And is there a winter one as well?
There's no winter one as far as I know because the break's too short.
Yeah.
But you can, I mean, do you guys have to organise any internship as part of your program specifically, like 60 days? So you may be able to do that through Monash without doing the actual summer research course. I'm not sure. I've only been at Monash since November, so I don't know all of their policies.
Yeah. Monash tell you to get an internship yourself there.
Yeah. So we are happy to take, especially in internships, we're happy to take anyone who's got 2 brain cells to rub together. Fortunately, we have to have them insured, so they have to be through Monash in some way.
Yeah.
But you are definitely more than welcome to come by, see the lab, and we can talk about what kind of projects would be good for you.
Yeah.
Cool. All right. I'll give you my card. Take it from you.
How do you actually suss out regulations for a device that doesn't exist itself?
How do you do? Yeah, that's difficult, and I don't know the answer for that because fortunately I haven't had to solve that problem. I think the most important thing, again, is just to show that it actually improves people's lives. So you have to be able to show that there is a clinical advantage to having your device compared to the current gold standard. And I think that would be the way that you would be able to get through something. So like, for instance, if you invented, you know, a brand new device that was using completely unknown principles, all you would have to do is show the benefits, I think, and then you should be able to get it regulated. That being said, sometimes regulation can just kill these things.
So for example, if you're integrating, if you have like multiple devices that, for example, like I'm doing the inhaler topic, so you have devices that measure things individually, but you don't have devices that measure them together. So
yeah, so that's not a problem, because you can show that previously all of these devices have been approved and worked, and actually there are some routes to market whereby if you can show that this device is similar to another one on the market, it's easier to get approved than if it's something that's completely new.
But the weird thing in my case, when we actually did the research, we found that most of the devices that are available, like they're not FDA approved.
Okay.
So they're like there are devices, but they're not FDA approved. The devices are there, but they're not in the market.
Yeah. So what you would do in that case, I think, is you would create your system, which is a series of devices, and then you would push the whole thing at once. That would be the better way, because otherwise you would have to individually get each device approved, and then you would still have to get your whole system approved anyway. So, and that's something that they actually look at in medicine is like the indications and counter-indications. So what two devices shouldn't be used together, what devices can be used in combination together, things like that. I'm not as familiar with that part of the thing, of the regulatory process, but I am aware that exists.
So what does your startup do? Like, apart from what does your startup do?
My startup, my lab. I work in a research lab, so we do mostly research on VAD and ECMOs. So we look at controlling VADs, improving the cannula, which are the tubes that connect to the device to the patient. We do experimental and numerical simulations for those who are interested in numerical. And we also do, so we look at a whole different bunch of ways to improve the devices, from looking at both a device standpoint, design standpoint, all the way to a medical management. How can we improve the medical management of the patient by improving protocols and things like that? So like that's our whole jam, is to just try and make these devices better and safer in any way that we can possibly think of.
So are you actually are you working on like a new device, or are you just seeing existing devices and doing clinical management on them?
So we don't work on new pumps, for instance. So for VADs, we don't work on new VADs, but we do work on sensors for VADs, or we do work on, so for ECMO, we're not trying to design a whole new ECMO pump, because it's just a pump. And so what we want to do is we want to do, for instance, one of the big studies that I'm doing at the moment is I'm adding sensors to ECMO circuits to automate the control of ECMO, how much oxygen goes into the blood and things like that. So we're looking at augmenting the systems. That being said, we are doing some devices. For instance, one of Sean's commercializations is a new way of attaching the VAD to the heart, which is in of itself a device. But the devices that we're doing are more mechanical, because it's easier to get translated. We don't actually have the funds at the moment, until we come up with some brilliant idea that someone's going to give us $10 million to do, to translate a full device through TGA. We're mostly trying to do effects change through clinical changes. So like I told you about that flow estimator. One thing I didn't tell you in that, which I probably had time to talk about, was there are actually two ways of attaching the RVAD to the right side of the heart. One is to reduce the speed to compensate for the lower pressure in the lungs. The other one is to put a little banding around it. And we compared the estimator between reducing speed and banding. We found that under banded condition, the estimator worked worse than reduced speed. So then the next day we went to our surgeon and we said, you should be reducing the speed, not banding it, and you'll get a better outcome from that. And in one day, that changes the outcomes of patients.
So wait, is that the LVAD or the RVAD?
So there is only LVADs commercially available. There are no RVADs.
So why is there no RVADs commercially available though?
That's a very good question. The answer is typically because it's been too hard. Okay? So at the moment, so when we first got LVADs out, and this this is really interesting. People actually told us that VADs would never work. Okay, so there were people out there that said you can never create a rotary VAD; it will never work ever. And so the people who started my scientific society, they were the people who said, yes, we can do it and we will do it, and they did do it. So just getting LVADs into people was so hard that it's only been in the last maybe 5 years, 10 years that they've become, have really become the convention rather than an experimental new therapy. So it's only been in the last 5 years that we've found patients are getting right heart failure because of implanting the LVAD. It's not because their heart's just getting naturally sicker. The LVAD is actually causing right heart failure, so we need something to replace to augment the right ventricle. So the answer is over the last 5 to 10 years, people have been developing RVADs, but they haven't become commercially available. So at the moment, people just use LVADs as RVADs and then modify them as necessary. So it takes so long to get a new device.
But is it difficult in the sense, in terms of operationally, is it difficult, or is it just for the approval process?
It's just the approval process. So from woe to go, you have to jump through so many hoops that it just takes time. Even if there is a clear and present clinical need for this thing, you've still got to go through all of the rigorous approval processes. So that has genuinely been it. I think RVADs will be out in the next 3 to 5 years. Everything in science is in the next 3 to 5 years. But there are some companies that are quite close, and also they're looking at, there's a huge interest in what they call the total artificial heart, which they just cut the whole heart out and then just put a pump in. So that one's definitely coming in the next 4 years. That the guy that is inventing that, or is inventing a new version of that, is Sean's old PhD supervisor. So he worked in our lab for ages.
But all this, I mean, it depends. If it's like a closed loop system, it's fine. But then if you're going to have like interfaces where it's going to communicate with another device externally, then you got to set up some protocols in terms of which device it can communicate.
Yeah. So at the moment they're completely closed circuit, and I think they'll probably stay that way. But because I mean, even the good thing about the VAD is anything you need to put in it, you can put it in a controller. So if you wanted to put like a pressure sensor in it, you could just integrate that in a controller, and then there's no wireless. The great thing about the VAD, which is also a terrible thing about it, is it has a drive line which goes outside the body and connects, so you don't need to do any wireless, so you don't have to worry about hacking or anything. The only problem with the drive line is, obviously, you've got a line hanging out of you, and it's bad for infection.
And they still haven't solved that issue with the drive line sticking out as a...
No, so they've developed some TET system, which is like one coil under the skin, one coil over the skin, like wireless phone charging. But it's the efficiency isn't good enough yet that they would trust a patient's life on it. So, but it may or may not come. I don't know whether people will ultimately accept TETs or not. I don't know.
I mean, it's all about. I mean, once you make a device, it's all about people accepting it at the end anyway. So.
Yeah, absolutely. You can make the most perfect device ever, but if no doctor uses it, then it's useless. That's no worries. I won't be giving next week's lectures, but it will be another guest lecture. So it's one of the other lecturers. I don't know them personally. Yeah, but bye now.